This is a short demonstration of proof of concept with continuous integration of Frama-C and Contiki-NG. First, I will show you how to move specifications from the verified source code to the Contiki-NG repository. Next, I will show you how to handle the differences between the verified source code and the original source code. And finally, I will give you a brief view on the whole continuous integration process. Let's start from the beginning. Here you can see two folders with verified source code ASCCM and with the original Contiki-NG repository. And we need to somehow move specifications from the ASCCM folder to the Contiki-NG sources. Of course, I can do it manually, but I will use a special tool called merge to automate it. This tool is a part of the toolset that we use for writing SSL specifications for a Linux kernel code. Let's just use it. I need to point it to the files with specifications and to the Contiki-NG repository. It's not mandatory to use to specify precisely the files here. Of course, I can just use directory, but this demonstration requires but for demonstration I will use a concrete file here. So this tool will try automatically to move contracts, to move in-body assertions and loop invariants to the repository of Contiki, and sometimes it will fail to do so, and in this case it will call external editing tool and will require some manual source code inspection from you. Here you can see a tool called Meld. It's external freeway merge tool, and on the left pane there is an original source code of the setk function from the Contiki-NG repository. On the right pane it is the verified source code of the setk function, and in between the tool tries to merge these differences between these two versions, and sometimes it detects and do it as we want. For example, it moves manual assertions, loop assertions automatically, and sometimes it confuses and fails to do so. And for example, in this case I want to save the original code call to the memcopy function, and we'll just remove these loop invariants. Later I will show you how to handle this difference between the verified source code, because this call was replaced by the loop, and we need to save and proceed next. Again, a small difference. In the verified source code there is a comment stating that the Frama-C will not be able to prove all verification conditions for this particular function, and in this case the merge tool gives a priority to the original source code, and I will not modify it. Next. Here you can see that loop assertions were moved and everything is okay here, except the small difference. The verified code, the right shift was replaced by multiplication, but I want to save the original right shift here and will not edit it. Next. Again, the assertion was automatically moved, and in the verified source code call by the function pointer is replaced by a direct call of function. And the merge gives a priority to the original source code, in this particular case, and I want to save it. Again, later I will show you how to handle this difference. Basically that's all. Let's take a look. The source code in the Contiki-NG repository was modified, and as we can see that the contracts were moved automatically. And here we can see the original call to the mem copy in the setk function, and the right shift here, and everything is okay, except I will manually remove these requires because Frama-C can handle functional pointers, and it will fail to process this contract. Perfect. Next, we need to somehow run the Frama-C with double VP and RTE assertions on the source code of the Contiki-NG repository, and we will use another tool that will single out a function from the whole sources with all its dependencies, and later, after that, we can run the Frama-C and try to prove and discharge all proof obligations. Let's just show it. The tool is called extricate. Again, you don't need to precisely specify the file here. The tool will extract to a single file function encrypt from the Contiki-NG sources. Let's do it. And now we can see the results. So for the encrypt function. Here we can see that all macroses, type defs, global variables were extricated from the source code, and even calls with contracts, and the encrypt function with specifications itself, and of course the right shift here. And let's just, after all these steps, we can run the Frama-C, and of course it will fail to discharge some proof obligations because of the bitwise shift. How can we handle this difference between the original source code that contains the right shift and the verified source code with multiplication? We will use the tool called Cosinel. It's developed in INRIA by Julia Lavol. It's a semantic patching tool, and I will write a simple semantic patch that will replace all shifts by multiplication. The patch can be very simple. For example, every identifier with the right shift will be replaced by multiplication. We can apply the patch to the encrypt function, to the extracted source, and it will be patched automatically. And now the basic idea here is to extract the source code, apply the semantic patch to handle the differences between the verified source code and the original source code, and after that, of course, you can run automatically Frama-C. Let's just do it. Here is another configuration for the extricate tool. We add additional arguments to apply the patch and to run the Frama-C. This is a wrapper script. So let's just see the results. Here we can see that the encrypt function is extracted, and after the patch is automatically applied to the source code, and after all, the Frama-C with WP and RTA assertions is called, and we can see that the all proof obligations were discharged. It's just a simple wrapper script, and it detects that if it detects a pattern of proved goals, and if proved goals is equal to the total, it outputs that the function was proved. This is a basic cycle for the continuous integration, and now I can show you the other semantic patches that I will use for other functions. For example, to replace a functional pointer in the sources, we will use this simple patch. To handle memcopy, we will, for the setk function, we will use this patch, and it removes the call to the memcopy and inserts the for loop with loop invariant, and a more, of course, multiply. And even if you want, for example, to add ghost arguments to a function, you can use you can use this semantic patch. COSNL is a very powerful tool, and it's enough to handle all differences between the verified source code and the original source code of the Contiki-NG repository. After that, of course, we can write additional configuration to the extricate tool. For example, we will apply universally multiply patch and patch for the functional pointer. For the setk function only, we will apply memcopy patch, and for the list init function we will apply we will try to add the ghost arguments, and after all, for every function we will call Frama-C. And another configuration file, it's just a list of verified functions. After all, we can run the extricate tool to extract every function from the Contiki-NG repository, apply the semantic patches on them, and call Frama-C. Let's just observe the results. For example, it extracts this function, tries to apply a patch, but there is nothing we can change in the body of the function, and Frama-C fails to discharge some proof of obligations because of assigned integer overflow. Next, other function, setk, I guess it was proved. Now our result, yes, it tries to proof encrypt, and here the functional pointer was replaced by the direct call of the function. Well, that's a basic idea for the how to run Frama-C on the repository. Now I can show you how to pair with GitLab this kind of workflow. Everything is the same, except after we can output just results of verification attempts here. Let's just retry and to view it again. This semantic patch should not be viewed as a permanent solution. We should be viewed as a temporal solution before either the developers will accept the changes to the mainline code of Frama-C+Contiki-NG repository, or before Frama-C developers will update Frama-C to handle such difficult code patterns. And basically that's all. I was trying to give you very high level overview of this concept, of this proof of concept, and I was trying to be as short as possible, and now we will see the final results here. Okay, thank you, that's all.